the graphs get steeper as the value of x goes on increasing. Let's analyze the curve representing y is equal to x cubed. For different values of x, the values of y are as shown. Observe that the value of y increases with an increase in the value of x. Consider another function y is equal to x raised to the power 5. Here we see that as x increases from 1 to 2, f3 of x increases from 1 to 2 cubed, and f5 of x increases from 1 to 2 raised to the power 5. Observe that for the same increment in the value of x, f5 of x increases faster than f3 of x. This change is quite evident if we take higher powers of x into consideration. In general, the value of y is equal to fn of x increases as n increases for n is equal to 1, 2, 3, and so on. Such a statement is true for all positive values of n, where fn of x is equal to x raised to the power n. Here, we can say that the growth of polynomial function depends on the degree of the polynomial. That is, the higher the degree, the greater is the growth of the polynomial function. Now, look at another function, y is equal to f of x is equal to 3 raised to power x. Here too, an increase in the value of x from 1 to 2 implies an increase in the value of f of x from 3 to 3 squared. Observe that function f of x increases faster than function f3 of x, with an increase in the value of x from 1 to 2. Thus we can say that for any positive integer n and for any positive value of x, the increase in f of x is equal to n raised to the power x is larger than the increase in fn of x is equal to x raised to the power n. In all the functions, the graphs grow as the value of x increases. Such types of functions are called exponential functions. Mathematically, an exponential function with a positive base b greater than 1 is a function defined by y is equal to f of x is equal to b raised to the power x. Exponential functions with base 10 are called common exponential functions. For example, f of x is equal to 10 raised to the power x is a common exponential function. Exponential functions with base e are called natural exponential functions, where e is equal to the sum of the series 1 plus 1 by 1 factorial plus 1 by 2 factorial plus 1 by 3 factorial, and so on. F of x is equal to e raised to the power x is an example of a natural exponential function. Do make a note of some features of exponential functions. The domain of exponential functions is the set of all real numbers. The range of exponential functions is the set of all positive real numbers. Graphs of exponential functions always grow upwards as we move from left to right on the x-axis. Graphs of exponential functions are close to the x-axis, but never touch it for any large negative values of x. Point 0, 1 is always on the graph of any exponential function. This is because b raised to the power 0 is always 1 for any real number b greater than 1. Let's consider an exponential equation b raised to the power x is equal to a, where b is a real number greater than 1. In logarithmic form, this can be written as shown here. This is read as logarithm of a to base b is equal to x. Mathematically, for a real number b greater than 1, the logarithm function is defined as log of a to base b is equal to x if b raised to the power x is equal to a. Take a look at the logarithmic forms of some exponential expressions. Clearly, we say that the logarithm is a function from positive real numbers to all real numbers. In other words, the logarithmic function log to base b is a function from positive real numbers to real numbers such that for all x belonging to the set of positive real numbers, there exists a real number y such that log x to base b is equal to y if b raised to the power y is equal to x. Logarithms to base 10 are called common logarithms. Logarithms to base e are called natural logarithms. For convenience, we do not write the base of natural logarithms. In other words, if the base is not mentioned, then it is considered as e. The figure here shows the graphs of logarithmic functions to the base 2, e, 3, and 10. Note some facts about logarithmic functions. The logarithm of a non-positive number cannot be defined. Hence, the domain of a logarithmic function is the set of positive real numbers. The range of a logarithmic function is the set of all real numbers. Point 0, 1 is always on the graph of any logarithmic function. Graphs of logarithmic functions grow as we move from left to right on the x-axis. Graphs of logarithmic functions are close to the y-axis but never touch it for any small positive values of x. Graphs of y is equal to e raised to the power x and log x to base e are mirror images of each other reflected in the line y is equal to x. Let's now see some important rules of logarithms. The change of base rule states that log p to base a is equal to log p to base b divided by log a to base b. Let's verify this. Let log p to base a be alpha, log p to base b be beta, and log a to base b be gamma. This implies that a raised to the power alpha is equal to p, b raised to the power beta is equal to p, and b raised to the power gamma is equal to a. From equations 1 and 3, we get p is equal to b raised to the power gamma into alpha. Now, from equations 2 and 4, we get b raised to the power beta is equal to b raised to the power gamma into alpha. This implies that beta is equal to gamma into alpha. Alpha is equal to beta divided by gamma. Therefore, log p to base a is equal to log p to base b divided by log a to base b.